Okay, so the answers are pretty straightforward. All you have to do is to count. What is the probability that a randomly drawn card, you pick one card out of the standard 52 deck, 52 card deck, and the answer is you have 4 kings out of 52. And so that's 1 out of 13. You could also say you have 1 king out of 13, you know, in each of the suits. So it's 1 out of 13. That's the same thing. How about if you pick one card and that happens to be a spade? Well, there are 13 spades or spade cards out of 52, and that's 1/4. And again, this is typical. I mean, this is simple because you have 4 equally distributed suits, right? How about the queen of clubs? How many queen of clubs are there? Well, we have 4 queens in the deck, and we have 13 clubs, but the queen of clubs is very specific. That's only 1 out of 52, right? And how about 7, 8, or 9 of any suits? And you have 4 of these, and you have 4 8s, and you have 4 9 cards. And so altogether, you have 12 out of 52, right? And so that is the answer to this particular question. And by the way, you can simplify this. You can reduce this to 3 out of 13. And again, simply because you're picking 3 numerals or 3 numerical values out of those 13 cards in each suit. Okay, all right, so hopefully this is all clear. All right, now let's go into 2 sort of advanced topics in probability, not really advanced, but 2 topics that are slightly more advanced than these basic probability questions. And this is where the critical applications come in place, all right? We talk about conditional probability, and then we talk about this false positives and false negatives, which are crucial. I think they are very important. Okay, so 2 events are called independent. What do we mean by independent events? Independent events, if they do not influence each other, okay? So for instance, you flip 2 coins and a card is drawn followed by a roll of die. Okay, let me just talk about this 2 coin tosses. You flip a coin and you flip another coin, right? And then you have tails, 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 heads, heads, tails, and heads, 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 right? And so one coin is not influenced by the other coin, right? So these 2 coins are totally independent. That's what we mean by independent events. This first one could be tails or heads, and this second can also be independently tails or heads. So those are 2 independent events. When you draw a card from a deck of cards, okay, and followed by a roll of a die, okay, remember the die, the result of this die roll is totally independent of the card you pick, because regardless of which card you pick, the roll of a die is independent. So that's what we mean by 2 independent events, okay? When events are independent, you multiply the probabilities. And by the way, let me illustrate something that's not independent, okay? Let's say you have bag of candies. Let's say you have 5, what do you want? 5 Skittles or something, okay? And the first person picks 1, okay? And then the second person picks 1 without the first one replacing this one that he or she picked, right? The second one is actually dependent on what this person picked, okay? So let's say out of these 5, 1 was the favorite one of the second person who picks, all right? If this first person picks that favorite one, then the probability that the second child picks his or her favorite one is 0, because that one particular one is gone, right? Whereas if this is not picked first, then the second child still has a positive probability of picking his, the favorite one. So the second pick depends on the first pick, and so that's not independent. That's called dependable. It's called a dependent event. Right, so that's the difference between independent and dependent events. But the point here is if 2 events are independent, then you end up multiplying probabilities. Okay, so for instance, find the probability that you get a tails and a queen when you toss a coin and draws a card. So you toss a coin and you draw a card. What is the probability that you get a tail? That's 1/2. What is the probability you get a queen when you draw a card from the standard deck of cards? That's 1 out of 13. And so what is the probability that you get a tails and a queen when you toss a coin and draws a card? And the answer is you multiply these two fractions, and the answer turns out to be 1 out of 26. Okay, so that's how you can calculate the probabilities if two events are independent of each other. All right, now the conditional probability is a sort of sophisticated idea which happens when certain things are conditional, all right? And this happens a lot with empirical probabilities. So let me illustrate this, and this is a pretty important example. I want you to pay close attention to this. This really is a something that you will see in terms of like, is there a bias, or is there a disproportionate impact, or is there an equity gap? These questions are addressed in like almost every workplace and every school and in every kind of a situation where people gather and lots of people are involved. Okay, conditional probability. What is a conditional probability? We denote this with probability of A with a long vertical line B. And this means the probability of A assuming that B is true. We read this as probability of A given B. So here, what we are doing is we are assuming that the B has happened or B is certain to happen. And given that B will happen or B is assumed, what is the probability that A also happens? Okay, so it is the probability of A given B. In other words, probability of A assuming that B is definitely true or B has occurred. Right. And here's the formula. You don't really need to memorize this formula, but the probability of A given B is the number of ways A and B occur, okay, divided by the total, divided by the number of ways B occurs. And I'll illustrate this because this is very abstract in the way the formula is stated. So the denominator is the number of ways B occurs. Now the reason the denominator, which represents the universe, is the total number, is because we are assuming B has occurred or B will certainly occur, right? So the denominator, which represents everything, is now the whole assumption that B has occurred, which is just counting not the entire total number of ways anything could occur, but the total number of ways that B could occur. And then the numerator is because B has to occur, and you want A to occur also. The numerator, the top is the number of ways A and B occur. All right, so here's a table, and this is a great illustration. You should study this carefully. Let's say in a department of motor vehicles, which is probably your favorite place to visit, driving test results for an August, for a particular August in some year, right? So both men and women go to take the driving test at this DMV. We had 35 men pass the test and 55 men failed. Totally 90 men took this test in August at this particular DMV. 45 women passed, 65 women failed, and that's a total of 110 females who took this test. So altogether, we have 200 people taking driving test at this particular DMV. This is totally a fiction. All right. Now, the question somebody is asking is there a sort of disproportionate impact? Is there a bias against a man or women, in this, based on this data? That's the kind of question that people will be asking. And the answer involves, of course, conditional probabilities. All right. Now, what is this? Oh, I don't have, okay, yeah, F. Okay. What is the probability that a person failed? You see that? Well, you have a total row here. So you have in total, by the way, this is not asking if the person is a male or female. What is the probability? And I hope you understand how to read this. This is asking for the probability of F, which is failed. What is the probability that a person failed the driving test, regardless of if the person was a male or female? And the result, the question is 120, Well, the answer is 120 people failed out of 200. And that's exactly the numbers that you should enter here. Okay, 120 divided by 200, and that turns out to be 0.6. That's 60%. Okay, so you can make the statement 60% of all the people who took this test in August at this DMV failed. What is the probability that the person failed given that what? Read this carefully, given that the person was a woman. So out of these women now, you have to look at, remember the denominator is what is the number of women who took this? That's 65. And out of those, sorry, that's not true. How many women took this? Yeah, the answer is 110. Okay, so you have to look for the right number. The number of women who took this test was 110, and out of those, 65 of them failed. So the probability that the person failed the test, given that it was a woman, is, notice here the numerator is number of women who failed. It's both women and failed. It's sort of an intersection, right? 65 people, women who failed out of the 110 women who took the test. And so this turns out to be 59%. Okay, so you can say 59% of all women who took the test failed. How about the probability of, and this is, be careful here, what is the probability that the person was a woman given that the person failed? Okay, you see the difference here? This particular, the first one here says, what is the probability that the person failed given that it was a woman? So in other words, out of all the women who took this, how many of them failed? What percentage failed? This one is a different question. This is asking what is the probability of W given F? What is the probability that the person was a woman given that the person failed? Okay, so out of all the people who failed, that's a denominator now. Where do you find that? All the people who failed. That's right here, okay? So that's what you have to have in the denominator. Of all the people who failed, 120, how many of them were failed and were women? And the answer here is 65 in the numerator. And this number is slightly different. That's 54%. Okay, so the conditional probability, let's review this. The conditional probability that the person failed, given that it was a woman, is 59%. But the probability that the person was a woman, given that the person failed, turns out to be 54%. Okay, what is the probability of what? A man given failed, all right? So what is, among all the people who failed, that's 120, what is the probability that it was a man? So you look for the number of men who failed, that's 55. And the answer here is 46%. Okay, these are the information that you will need in order to compare and study if there had, if there was any kind of a bias or a disproportionate impact. And I don't know. I mean, you have to then go and ask, the equity experts about any kind of a disproportionate impact. Looking at these two numbers here, maybe there was something. Out of all the ones who failed, bunch of people, 54% are women, 46% were men. It doesn't seem like there's a huge gap here, but that's something that a person can ask. All right, that brings us to this very last and probably the most important of applications of probability. Now, I will be asking you questions like this, both on homework and on your exams, right? And I will be asking questions like this in your homework and also on the exam that is going to cover this section. So learn how to do this, okay? It's very important for you to be able to do what I'm about to do. I'll try to explain all the details, and you may need to review this kind of thing as you do your worksheet. All right, so here's table 2. Suppose 2% of the population are infected with a certain virus. Okay, 2%, not a very common virus. It's a rare disease, possibly. Okay, only 2% of the population are infected with a virus. Test is, by the way, no test is 100% accurate. So this particular test is said to be 90% accurate, which means that 90% of those who actually have the virus will have the positive result, but 10% will not. The 10% of the people who carry the virus will have the negative result. And if you're not infected with a virus, again, 90% of them will correctly test negative, but 10% will test positive. Get that? That's all you need in order to completely fill in the blanks here. Okay, let's go ahead and do that. If you're tested positive, how likely are you? This is a question that we will address at the end. Now, by the way, there's a very sophisticated formula called Bayes formula and Bayes theorem that would help you, but it's really, really hard to apply. Okay. In fact, a bunch of medical schools have tried to teach that to a bunch of smart medical students, and many of them don't get it. All right. So here is a much better approach. Okay. Remember, one of the strategies for problem solving is, try to apply this to a simple situation. Like when you buy and sell many times, or when you have different percentages involved. A good idea is to start with a fixed number, a nice fixed number. And that's exactly what we will do here. All right. I'm going to start with 1,000. That's a nice round number. Okay. Now, a problem of a chart like this will be given to you, and you just have to fill out the numbers. Let's go ahead and fill out these two numbers, or fill in these two numbers. Infected. How many people are infected out of 1,000? How do you know? Well, you're given that 2% of the population are actually infected, right? So 2% of 1,000 is 20. All right, let me go ahead and write this. It's 1,000 times 0.02 because 2%, and that's 20 people. All right, and then the rest, which is 1,000 times 0.98, 98% of the population, that's 980 people, don't have the virus. Okay, so I'm going to number these so that you can tell in which order I am filling in these blanks. Okay, so these total numbers are the first things you will do. All right, next, out of these 20 people, and these are, by the way, all 20 are infected. Okay, that's the assumption. The test, 90% accurate test, is going to make sure that 90% of these, so let's go ahead and do this. Out of the 20, 90% of the 20 virus carriers are going to test positive, and that's 18 of them. Okay, and so that means the rest of them, now you can do 20 minus 18, or you can do 20 times 10, 10%. Okay, either way, you will get 2 people. Now, who are these 2 people? Let's try to figure out. These are the 2 people who actually have the virus, but unfortunately, because the test is not 100% accurate, these people will get a negative result. Now, this is called a false negative. Very, very bad situation, because these people actually have the virus, but somehow the test says, you're okay, you're free to go. Go eat a buffet or something, and they spread the disease. All right, so that's 4. And then let's say number 5. Maybe I will go to 5 here, okay? The test is, okay, so the test is applied to these 980 people who don't have the virus, okay? But, and 90% of them will test negative correctly, right? So 980 people don't have the virus, and 90% of them will test negative, because that is the correct result for these people. And that's 882 of these people, okay? But unfortunately, out of these 980 people who don't have the virus in reality, 10% of them will test positive because the test is not 100% accurate. That's 98 people. Okay, so I hope you followed me as I filled in these 6 blanks. You start with the total numbers here, okay? And then these 2 columns are, you multiply by 90% here for the positive case and 90% here for the negative case. And so that's how you apply these. Okay, now you get to add these numbers. 18, okay, so let's say this is number 7. Okay, so you add 18 and 98 to get the total, and that will give you 116. All right, number 8, you add these 2 numbers, so it's 2 plus 882, and that's 884 people. And of course, these 2 numbers together have to add up to 1,000, because that's the total number. Okay, so what does it say? Okay, so hopefully you have seen exactly how I filled out or filled in each of the boxes, right? Okay, out of 1,000 people. Um, and what does this story tell you? This is of particular importance, okay? Because I want everybody to understand the implications of false positives and false negatives. These two are the most unfortunate people who actually have the virus, but somehow they test negative, and so they think they're okay when they aren't, okay? So they will not get treatment, and that's dangerous. These false positives are not as bad. I mean, okay, so these 98 people will test positive even though they don't have the virus. So they will have to do re-examination or recheck or something, and hopefully next time they'll get the right result. But what this chart is telling us is this. Okay, ready for this? Out of the 160 people with positive test results, okay, only how many people are really have the virus? Right here, okay? Only 18 of them have the virus. All right, so 18 out of 116. This turns out to be, let's see, do I have the number? 18 out of, 18 out of 116 turns out to be 15.155. I'm going to cross out this page number. So that's about 15.5%. What this is saying is, if you test positive for this rare virus, okay, if you test positive, only 15% of those people who test positive actually have the virus. Most of them don't. Okay. Now, how could it be so wrong when the test is 90% accurate? Well, because there are a whole lot of people who have no virus as opposed to people who do have a virus. So the fact that this is very disproportionate affects the number of false positives to be a much larger number than the people who actually have the infection and test positive. And so, and sometimes, by the way, the doctors will test you for a rare disease, and then the test comes out positive. And then they will say, oh, don't worry about that. It's only the first test. And you're like, what do you mean, don't worry? This is a serious problem, right? I mean, I may have this disease or whatever. But the reason they say it's not so worrisome at the beginning is because even though the test could be very accurate, the probability of the positive test result as a false positive is actually quite high. In this case, what's the opposite of what's 100% minus 15.5%? That's like 84.5% chance of false positive. Okay, and so you don't have to freak out when the test result first comes out to be positive. Now, just on the historical lesson, about 30 years ago, there was, maybe 40 years ago, there was a big crisis called the AIDS virus. People had never seen the AIDS virus or HIV virus. And that was once upon a time called a incurable disease. And basically everyone who had the virus and who had a symptom ended up dying. And so some people would test positive, and then they just freak out, and they'll just start to get completely depressed and so on. While many of those were false positives, they actually didn't have the virus, but the test says they did. And so to know something like this is really, really important in my mind. Okay, so practice this kind of a problem in your homework and on your worksheet, and hopefully you will get to learn this important concept of false positives. Okay, so back to Vegas. I hope you understood how important it is to know and understand probabilities. And so work on the worksheet number 10. And then next time, I hope you have also learned how important it is to count, or to be able to count. And sometimes that counting is very tricky. So that's what we will be learning in lesson 11. All right, so until then, I hope you have a great day, and see you then. Bye.